So before we do these two problems, you've got the tests back now, and now that you have the tests back, you can redo the ones you got wrong and turn them back in. Just make sure that when you redo them, you show your work. And I give you up to half your points back for those. So that means like an 80 turns into a 90 if you redo those problems. If you're not sure how to do them, you can work with a classmate if you want to, or you can come in and talk to me. And I would be happy to sit down with you and work through them problem by problem if we need to. So make sure we have all those correct at some point so that you can get back as many points as possible. Usually I say within the next week or so. Okay, so now with that said, before we do these two problems, to this point in the course there's 138 points possible. Now, since this course is required to get you into the next level course, passing is considered 80%. So out of 138, you need 110 total points right now to be considered sitting solid for a C in the class. So if you check on Blackboard, it should clearly state what your total points are at this point. So make sure you're checking that out, and if you're below that, one, make sure you do corrections on the tests, and other, if that's not going to get you close to it, come talk to me and we'll see what we can help you out with to get you up to that level.
Do you want us to give these back? We're going to take them.
They are yours. Take them home, hang them on the fridge if you'd like. Like I said, work on any of the ones you got wrong and get them back to me. I mean, you're not going to hang it on the fridge for all the family to ooh and ah over? Okay, so for this one here, where do we start? Okay, so 5x and 3x make 8x. So we have 8x plus 9 equals 33. What's next? Subtract 9, good. So 8x equals 24. Divide by 8. So x equals 3. Again, you could always go back and put the 3 in for x and make sure that you get the same value on both sides of the equal sign. This next one's slightly different. What do we have to do there?
Get rid of the smaller x.
Okay, we have to get rid of the smaller x. Since there's one on each side, we can't just combine them. We have to get rid of one. So we get rid of the smaller one, which is a 3x. That leaves us with negative 2 over here. We have to subtract 3x from this side. 8x minus 3x is 5x. Then what? Yep, plus 37. So all we have left over on the right is 5x. What's negative 2 plus 37? 35. Good. And finally, divide by 5. So 70. Okay. Good question. Could we subtract the 8x first and make this work? Absolutely. You get negative 5x minus 2 equals negative 37. The only big difference is you're working with a lot more negatives. Then you'd add the 2. Negative 5x is negative 35. And then you would divide by the negative 5. And negative divided by negative is a positive 7. Yeah, I always say take away the smaller one just because people tend to make mistakes with the negatives as well. Any other questions? Okay. Well, for today, you're starting Unit 2. Unit 2 does focus on fractions. But for the first day here, we're going to be looking more at these equations and problem solving. We're going to be looking at some rules of geometry and using then these equations to work with those rules of geometry. So we're going to start with one of the most, well, probably the most basic geometric concept out there. And that's just that right there. It's called a point. A point is nothing more than marking a location. Whether it's on the board here, on a table, surface, it's a location. If it's in three-dimensional space, it is simply a spot in space. It has 0 dimensions. So the first question that comes up is, what is a dimension? A dimension is a measurable direction. So like these tables, the top of these tables have 2 dimensions because you can measure them in 2 directions. The filing cabinets in the corner have 3 dimensions because they can be measured in 3 directions. Now the tables are 3-dimensional. I was just talking about the surface of the table is 2-dimensional. So anyway, how do we take this 0-dimension point here and give it dimensions? Well, what we can do is we can take that point and we can move it in a single direction. And what we've created here, it's often called a line, referred to as a line, but its technical name is a line segment. A line would continue on forever in both directions. The length of that line segment is equal to the distance that we move the point. Now we move that point in one direction, which means we now have 1 dimension. It is measurable in one direction. Or it can move back and forth in one direction if you want to look at it that way. Now we can take that line segment and we can move it in a second direction. Now a key word that we're going to come up with here is perpendicular. Perpendicular means at a right angle, but it's a little bit more powerful than that. It means at a right angle in every possible direction. Now, a right angle means a square corner or 90 degrees. So on paper, perpendicular just means right angle like that. There can be 2 lines going through each other. They can meet together. In 3 dimensions, perpendicular, if you're looking at a line coming out of the board, perpendicular means it comes out no matter what direction you measure the angle between the line and the board, it's a right angle. So perpendicular is just a little bit more powerful than right angle. So I'm going to take this line segment and I'm now going to move it in a direction perpendicular to the original direction. So in other words, I either go up with it or down with it and go perpendicular. So I'm going to go down. Now if you think about dragging a stick through the sand, it traces out a rectangle. That rectangle now has 2 dimensions because it's been moved in 2 directions. It now has 2 distinct dimensions, directions that it can be measured in. The size or area covered by that rectangle depends on the length of the original line segment, that across there, and then that distance moved. Ran out of space there, but that says distance. Now, a lot of you have seen the area of a rectangle defined as length times width, and that is strictly for a rectangle. I'm saying length times distance because there are shapes other than rectangles we can find the area of, so we're not necessarily always using the width. Most of the time we're using a length of some sort and a distance that goes with it. We're going to come back and talk more about areas in the second part of class. But let's, for now, go back to that point again. And this time, instead of going in a single direction and stopping, we're going to go in a single direction and we're just going to keep on going forever. This forms what we call a ray. It's a little bit outdated, but at one point, this ray would have been defined with a direction. Kind of like navigating. You have a coordinate system. This is the 0 degree direction. This is 90 degrees, and it goes around. So this ray, let's just say, I'm just going to give you this. Let's say it's going at 21 degrees is its direction. If I take that ray and I go back to the starting point of that ray, and I drag that starting point again in a different direction, I now have two rays that have a common starting point, and that common starting point is called a vertex. What I have formed here is called an angle. The size of the angle is equal to the difference in direction. So let's show you what I mean by that. So let's say this is still on the coordinate system. Notice the vertex is at the center of that coordinate grid. This is 21 degrees here. Let's say this second one is at 46 degrees. The difference in direction, 46 degrees minus 21 degrees is 25 degrees. So this angle here is defined to be a 25-degree angle. That is the technical definition of the size of an angle. Now, through the years, navigation as a skill has become something that fewer and fewer people are familiar with. Once upon a time, a significantly large portion of the population knew about navigation, knew about directions and stuff like that. So now, because of that, we've modified our definition of an angle a little bit. If I take and I make a complete turn, how many degrees is that? 360 degrees. That's a full circle. One complete turn. If I make a half a turn and end up going back in the opposite direction, how many degrees is that? 180. How did we get 180? Just half of 360. Good. If I turn and end up going at a right angle or square corner to where I started, that is 90 degrees. Again, how do we get 90 degrees? Fourth of 360 or half of 180. All these angles we're finding here, the 180, the 90, they are a fraction of 360 degrees. In other words, a fraction of a full circle. So now when we define an angle, let's say I look at this angle here and I say that that angle is 25 degrees. What we're saying is that that is 25 3/60ths of a full circle or a full turn. So that is the new modern definition of an angle. The measure of an angle is the fraction of a full turn that it is. Realistically, as long as we know these benchmarks, we're good to go. Okay, so I want to talk briefly about naming an angle. We mentioned this vertex here. we can name a point with just a letter. So I might call that point A. That's my vertex. A ray is named by that starting point and then any other point on it. So let's say I've got points B and C here. That ray there can be named ray AB, or it can be named ray AC. You must name the starting point and then any other point that's on that ray. And notice it does have an arrow, so A is at the starting point and B or C are at the arrow. Slightly different, let's say I had segment AB. So that just looks like that with a segment above it. It doesn't matter whether I call it segment AB or BA because there is no way to distinguish what's the starting point and what's the ending point for a segment. So I've got ray AB there. Let me put point D over here. That would give me ray AD on that side. To name the angle, we use this symbol. That's the angle symbol. And we give a point on one side of the angle. So it doesn't matter which side. So I have to give either B or C. So I'm going to give B. Then you have to give the vertex in the middle, which is A, then a point on the other side, so D. So this is angle BAD. I didn't really mean for that to come out like that, by the way. Or this could have been named angle DAB. Or I could have done C instead of B. It doesn't matter. A little bit of a distinction, by the way. If you see this, that's saying the angle itself. If they have that little M in front of the angle symbol like that, M, angle BAD, that's saying the measure. That's asking for how many degrees that is. What's that? Yeah, that's an angle. There. Okay. So now let's look at some special relationships with our angles. We can take and create an angle. If we go back to that same starting point and create a third ray, we now have, well, we're going to say two angles to begin with, but technically there's three. So let's say we have this first angle here that was 23 degrees. And we created another angle here that is 34 degrees. These two angles are what we call adjacent angles. Because they share one, they share the vertex, and two, they share a side. So if I'm going to list them, let's say this is I would say angle ABC and angle CBD are adjacent angles because they share the vertex B and they also share side BC. Because they are adjacent, they become additive. Additive means you can just do addition and subtraction operations with them. So if I wanted to find, I'll throw some terminology out here, the measurement of angle ABD. So that is this bigger angle on the outside. I can find that by simply adding together the two smaller angles. 23 degrees plus 34 degrees, which is going to give me 57 degrees. And the opposite is true. Let's say I tell you that this is 92 degrees here, and that this angle here is 131 degrees, and I want to find this one. Well, I know that the measurement of angle ABC plus the measurement of angle CBD has to equal the measurement of angle ABD. And I can use my basic algebra. Measurement of angle ABC we have is 92. Measurement of angle CBD, that should be not CBC. CBD is what we're looking for. We don't know that angle, but we do know that the measurement of angle ABC is 131. And now this is, if you think of this as being our variable here as being x, we're just solving an equation. We're subtracting 92 from both sides. So the measurement of angle CBD is 39 degrees. Now, obviously, you didn't have to write it out in an equation like this. I did that to prove a point. Basically, all you really have to do here is 131 degrees minus 92 degrees. And you get the 38 degrees. Any questions? So in your notes, I want you to find that angle there in blue. And then once you found that, I want you to find the angle here in red. So I'll give you a couple minutes to figure those out. So for our blue angle, how are we going to find that? Yep, we're simply adding those two together. 35 degrees plus 29 degrees gives us 64 degrees. Any questions on that one? For our red angle, then, what are we going to do? Perfect. We're going to subtract 152 minus 64 is going to give us 88. How many of you got both of those? Good deal. So now then there are some special relationships with these adjacent angles that we can deal with. One of those special relationships would look like this. We have two adjacent angles that add up to 180 degrees, or a straight line. One name for this is what we call a linear pair. When they're oriented like this, so that they actually do create a line, they're a linear pair. But a more general name for this is supplemental angles. They supplement, or they help each other to create a straight line. So supplemental angles add up to 180 degrees. Another special case would look like this. These two angles add to 90 degrees, or a right angle. And the special name for these is complementary. They are complements of each other. Now, if you're anything like me, when I first learned these, I could remember the words, but I struggled to remember which one was which. So I always say you get complements when you are right. So complementary angles add up to a right angle. So if I were to ask you to find the complement of 41 degrees, how would we do that? 90 minus 41 would be one way to go about it. 49 degrees, right? If we wanted to get more into the algebraic side of it, we would say x would be our unknown angle plus 41 has to equal 90. And of course, we would solve that by doing exactly what we did here, subtracting 41 degrees. X is 49. If I asked you to find the supplement of 23 degrees, how would we find that? Yeah, 180 minus 23 is going to be 157, right? Or we'd say x plus 23 has to equal 180, and we'll solve it by subtracting the 23. Any questions? As a result of these special cases we've seen so far, we can create a special case that looks like this. So if I tell you that this angle here is 68 degrees, I want to know what is this angle here. Well, let's go through it step by step. This, of course, is a straight line. So how would we find this angle here? 180 minus 68. So this angle is 112 degrees. Now this is also a straight line. So that means this angle and this angle are also supplements. So I would find this one by doing 180 minus 112. Gives us 68 degrees. These two angles end up being the same. There's several reasons why they're the same. They're both supplements to the same angle. They both make straight lines with 112 degrees, so therefore they have to be the same. If we were doing more formal geometry, we would talk about theorems and postulates. And one of those theorems is two angles that are supplementary to the same angle must be equal. We're not going to get into formal postulates and proofs and all that stuff. But these are what we call vertical angles. Vertical angles are opposite corners of intersecting angles, and they will always be equal. So if those two are vertical, these two would be vertical as well, which means this angle has to be 112 degrees. And again, it comes because they're supplementary to those other angles. Bless you. So now that we have all these relationships, we can pull the algebra into it. I should tell you this is a right angle. That square in the corner there is just a box. It's a square box, or it's a square. And that tells you that's a square corner. So it tells you that's a right angle. So anyway, what can we say about those two angles? They add up to 90. They're complements. So we know that 7x plus 2x must equal 90 degrees. And now we can find each of those angles by solving the equation. 7x plus 2x makes 9x. So 9x equals 90 degrees. And then divide by 9. X equals 10. Now we're not done yet. We haven't answered the question here. The question was, how big is each angle? Or find each angle. We know that x equals 10, so we have to come back up here. This angle is 7 times x, becomes 7 times n, or 70 degrees. This angle here is 2 times x, becomes 2 times 10, or 20 degrees. So here we might have 3x and 9x. What's the relationship between those two angles? They have to add up to 180. They are supplements. So 3x plus 9x equals 180. Then what? So here we combine 3x and 9x, make 12x. And then divide by 12. So x equals 15. Now again, we're not done. We have to go back and actually find each angle. This one is 3x. That's 3 times 15. 45 degrees. This one is 9x. That's 9 times 15, or 135 degrees. Any questions on any of those so far? So far, both of the problems we have done have taken the form that the measurement of one angle plus the measurement of another angle has to equal a total. So here, this takes on the same form, it's just a little more complex. What do these two angles have to add up to? 90. So 6x plus 7 plus 2x plus 3 equals 90. Now I should note, it doesn't matter what order we add these together. I could have done 2x plus 3 plus 6x plus 7. That wouldn't have made a difference. Now the first thing we're going to do is we're going to stay on the left side of the equal sign, and we're going to combine what we can. What all can we combine there? Okay, 6x and 2x makes 8x. Anything else? 7 plus 3 makes positive 10, so plus 10. Then what? Subtract 10. 8x equals 80, and then divided by 8. Good. X equals 10. Now, of course, we do still have to go back and find each angle. So this is 6x becomes 6 times 10 plus 7. So that's 60 plus 7 is 67 degrees for that angle. This one, 2x becomes 2 times 10 plus 3. 2 times 10 is 20. Plus 3 is 23 degrees. And just a simple check. Yes, those two do add up to 90, so it works out. So there's a case where two angles add up to a total. The other case we can have is we can have angles that subtract. The algebra is a little more complex on that, so we're going to skip over that. The third case is this one. Here, what's the relationship have to be between those two angles? They have to be equal. So here we have two angles that must be equal to each other, or two things that must be equal to each other. So we have 3x plus 28 must equal 5x minus 4. Where would we start on that? So we subtract the 3x. So 28 equals 2x minus 4, good. And then plus 4. So 32 equals 2x. And then divide by 2. 16 equals x. So now we know that x is 16. We go back and plug it in for x. So this becomes 3 times 16 plus 28. 3 times 16 is 48. Plus 28 is 76. So it's 76 degrees. This one better come out to be the same, but we're going to check it anyway. So 5 times x becomes 5 times 16 minus 4. 5 times 16 is 80. Minus 4 is 76. So we're relatively sure that that is the correct answer. In your notes, find these two angles.